Let's say you're a bank trying to figure out who's going to default on a loan. Or maybe you're a doctor trying to classify a tumor as benign or malignant. In both cases, the challenge is exactly the same. How do you draw a clear line that separates one group from the other? Well, today we're diving into a classic, super powerful technique for drawing that very line, linear discriminant analysis, or as we all know it, LDA. So here's our game plan. First, we'll tackle the core challenge of classification itself. Then we'll get into the really clever generative idea that makes LDA tick. We're also going to put it head-to-head with its close relatives, QDA and logistic regression, to see where it truly shines. And finally, we'll wrap it all up with a practical guide on when you should actually use it. Sound good? Let's jump in. You know, at its heart, classification is really all about drawing lines in the sand. It's about looking at a big, messy pile of data and finding a simple, clean rule to separate one group from another. Think about it. High-risk versus low-risk applicants, spam versus not spam. The goal is always the same. Find that perfect dividing line. So that's the million-dollar question, isn't it? Look at these groups of data. You could draw a ton of different lines to split them up. But which one is the best one? LDA has a really specific, really genius answer to this. It says the best line is the one that does two things at once. It pushes the centers of the groups as far apart as possible, while at the same time, it squeezes the data within each group as tightly together as it can. It's all about maximizing that class separation. That's its whole mission. And this is where LDA's unique philosophy really comes into play. You see, instead of just jumping right in and trying to draw a boundary between the classes, it takes a step back. It kind of acts like a detective. It builds a detailed profile for each group first. It asks, what does a typical member of Class A look like? And what about Class B? Only after it has these detailed profiles does it use them to calculate the perfect dividing line. This approach is what we call a generative model. It's not just about telling the groups apart. It's about actually understanding the story of how the data in each group was generated in the first place. Once it figures out the probability distribution for each class, it can use this powerful tool called Bayes' theorem to essentially ask, okay, given this new data point, which group's story does it fit better? It's a much deeper level of understanding. Now, to make this whole modeling task even possible, LDA has to make one crucial simplifying assumption. It assumes that the data inside each class follows a bell curve, or to be more technical, a multivariate Gaussian distribution. In plain English, it just pretends that each of our data clusters is a kind of elliptical cloud, with most of the points all bunched up near the center. This assumption, well, it's the key that unlocks everything for LDA. So here's how it all comes together in a few logical steps. First, we make that bell curve assumption. Second, we find the center or the mean of each class. This is the part that helps us push the groups apart. Third, and this is LDA's signature move, we assume that even though the centers are different, the overall shape and spread of those data clouds are identical for all classes. This shared shape, which we describe with a single covariance matrix, is the part we want to keep as compact as possible. Once we have those pieces, the math just spits out the optimal straight-line boundary. To really get a feel for LDA's strengths and, its weaknesses, let's compare it to its more flexible sibling, quadratic discriminant analysis, or QDA. They basically share the same DNA, but one tiny little difference in their assumptions leads to completely different results. Here is the fundamental difference. Remember how LDA assumed all the data clusters have the exact same shape and spread? Well, QDA just throws that assumption right out the window. It lets each class have its own unique shape, its own orientation, its own covariance matrix. And the result? LDA is stuck drawing a straight line, but QDA gets to be more flexible and can draw a curved or quadratic boundary. This quote absolutely nails one of the most important ideas in all of machine learning, the bias-variance trade-off. Think of it like this. LDA is like a stubborn, seasoned archer who always aims for the exact same spot. This makes their shots very consistent. That's low variance. But if the target moves, they're going to consistently miss, and that's high bias. QDA, on the other hand, is like a rookie archer who's always adjusting their aim. They might get closer to a moving target, but their shots are kind of all over the place. That's high variance. So what does this actually mean for you in practice? It's pretty simple, actually. If your data clusters really do have similar shapes, the true boundary between them is probably a straight line. In that case, LDA is your champion. QDA's extra flexibility will just cause it to overthink things and probably perform worse. But if your clusters have very different shapes and sizes, then the real boundary is probably curved. And in that scenario, QDA is the hero because LDA's simple, rigid approach just won't be able to capture it.
Okay, so we've seen how LDA stacks up against its flexible cousin, QDA. Now, let's bring another heavyweight contender for classification into the ring: logistic regression. They often compete for the same jobs, but trust me, their fighting styles are totally different.
What's interesting is that at the end of the day, both LDA and logistic regression can end up drawing a straight line to separate your data. The final result can look identical, but how they get to that line, well, that reveals a really fundamental split in their core philosophy. Okay, here's the difference in a nutshell. LDA, our generative model, is like learning to tell cats from dogs by studying everything about them: their fur, their size, their behavior, the whole shebang. It builds a complete picture of each animal. Logistic regression, on the other hand, is discriminative. It's like learning to tell them apart by just finding the one single feature that's most different. Like, does it bark or does it meow? It ignores all the other details and just focuses on finding that dividing line. And this philosophical difference gives us a crystal clear rule of thumb. If your data really does fit that bell curve assumption we talked about, LDA's deeper, generative understanding of the data gives it a huge edge. But if that assumption is way off, logistic regression, by not making those assumptions in the first place, turns out to be the more robust and reliable choice. All right, we've explored the theory, we've made the comparisons. Let's boil all of this down into a clear, actionable summary. When should you actually pull LDA out of your data science toolkit? So when is it LDA's time to shine? Well, it's a fantastic choice in a few specific situations. First, when you don't have a lot of data. Its simplicity and strong assumptions make it less likely to overfit. Second, when your classes are already pretty clearly separated. And of course, when you have good reason to believe that they actually do follow that bell curve pattern. In these scenarios, LDA can be a surprisingly stable and powerful performer. And this all brings us to a fundamental question that every data scientist, every analyst has to grapple with. The story of LDA teaches us a really valuable lesson. Simple models that make strong assumptions can be incredibly powerful if those assumptions are right. So as you tackle your next problem, remember that trade-off. Do you bet on the elegant simplicity of a model like LDA, or do you go for the raw, flexible power of a more complex one? The real art of data science lies in knowing which path to choose.